At exactly 9:50:45 Coordinated Universal Time on the morning of September 14th, 2015, two instruments on opposite sides of the United States, one in Louisiana, one in Washington state, separated by 3,000 kilometers, recorded within 7,000ths of a second of each other an identical, unmistakable signal. It lasted a fifth of a second. It rose in pitch and intensity, sweeping upward with unmistakable, escalating urgency, and then it stopped, abruptly, completely. If you convert that signal into audible sound, which is possible, because the frequencies involved happen to fall within the range of human hearing purely by coincidence, it sounds something like a low, rising chirp. Not dramatic, not explosive. A quiet, physical sound, almost unremarkable if you heard it in isolation without any context at all. That quiet chirp was the sound of space-time itself ringing. Here is what makes that sentence, and everything that follows from it tonight, genuinely extraordinary. This was not a radio signal. It was not light of any wavelength, not visible, not infrared, not X-ray, not radio. Every single observation we have discussed throughout this entire series, from the wow signal to the cosmic microwave background to the first photograph of a black hole, has depended, in one way or another, on detecting electromagnetic radiation, light, in its many forms, arriving at an instrument and being measured. This was something else entirely. This was a direct, physical ripple in the fabric of space and time itself, passing through the Earth, stretching and compressing the actual distance between two mirrors positioned 4 kilometers apart, by an amount so unimaginably small that describing it accurately requires numbers that strain ordinary language to convey. The signal had travelled for 1.3 billion years to reach us. It originated from an event that occurred long before complex life had even begun to emerge on Earth. The final, catastrophic collision and merger of two black holes, each several dozen times the mass of our Sun, spiralling into each other at velocities approaching the speed of light, in the last fraction of a second before they became one. Albert Einstein had predicted that such ripples should exist in 1916, exactly 1 century before they were finally detected. He himself was not entirely convinced they would ever actually be found. He doubted at various points throughout his own life whether the effect was even real, and separately doubted whether, even if real, it would ever be strong enough for any conceivable instrument to actually measure. Tonight we are going to trace the complete story of how humanity built an instrument sensitive enough to detect a ripple in space smaller than 1/10,000th the width of a proton, and how, on one specific September morning in 2015, that instrument heard, for the first time in the history of our species, two black holes colliding, 1 billion years before we existed to listen. Let's begin with the prediction itself and the century of doubt that followed it. Chapter 2. The ripple Einstein wasn't sure about. Discovery. In November 1915, Einstein completed the field equations of general relativity, the same equations we discussed in an earlier chapter of this series, the ones Karl Schwarzschild would solve from the trenches of the First World War within a matter of weeks. Those equations described gravity not as a force acting instantaneously across space, in the way Newton had understood it for over 2 centuries, but as the direct curvature of space and time itself, caused by the presence of mass and energy. The following year, in 1916, Einstein turned his attention to a natural, logical extension of his own theory. If mass and energy curve space-time, then a moving mass, particularly a mass undergoing acceleration, changing its motion in a complex, non-uniform way, should, according to the mathematics of the theory, generate ripples in that curvature. Disturbances that would propagate outward from their source, through the fabric of space-time itself, at the speed of light, exactly as ripples spread outward across the surface of a still pond after a stone is dropped into it. Einstein calculated that these ripples, which he termed gravitational waves, should exist as a direct, unavoidable mathematical consequence of general relativity. But his own calculations and his own subsequent thinking about the subject over the following decades remained genuinely uncertain and, at various points, actively contradictory. In 1936, 2 decades after his original prediction, Einstein and a colleague, Nathan Rosen, submitted a paper to a physics journal arguing, based on a more careful mathematical re-examination, that gravitational waves might not actually be physically real at all, that they could, under certain interpretations of the mathematics, be nothing more than a mathematical artifact, a byproduct of the specific coordinate system used to describe the equations, rather than any genuine physical phenomenon capable of carrying real energy through space. The paper was initially rejected by the journal's reviewer, who identified what appeared to be a specific technical error in Einstein's reasoning, a genuinely unusual and, for Einstein personally, evidently frustrating experience, since peer review of this particular kind was not yet standard practice in physics at the time, and Einstein reportedly resented the process considerably. The specific question of whether gravitational waves were physically real, capable of carrying genuine energy, and, in principle, being detected, remained a subject of serious, unresolved theoretical debate among physicists for decades following Einstein's original 1916 prediction. It was not conclusively mathematically resolved until a specific 1957 conference, sometimes informally called the Chapel Hill Conference, at which physicist Richard Feynman offered what became a widely influential decisive thought experiment, now generally known as the sticky bead argument, that persuasively demonstrated gravitational waves must indeed carry real physical energy, capable in principle of doing measurable physical work, even once their physical reality was more broadly, generally accepted within the theoretical physics community. An enormous, genuinely daunting practical challenge remained. Gravitational waves, according to the very same equations that predicted their existence, should be extraordinarily, almost unimaginably weak by the time they reached Earth from any realistic astronomical source. The specific mathematics suggested that even a gravitational wave generated by an extraordinarily violent, extraordinarily energetic cosmic event, precisely the kind of event we will examine closely later tonight, would, by the time it finally reached Earth after travelling across vast cosmic distances, stretch and compress the actual physical distance between any two objects by a genuinely infinitesimal fraction, correspondingly requiring an instrument of essentially unprecedented, almost unimaginable sensitivity to have any realistic hope of detecting it at all. For much of the 20th century, this specific practical challenge appeared to a great many working physicists to be functionally, perhaps even permanently, insurmountable. Detecting gravitational waves seemed to many like an idea that might remain forever confined to theoretical physics, entirely beyond any realistic experimental reach. It would take until the closing years of the 20th century and the opening years of the 21st for a small, determined group of physicists to finally, genuinely prove that assumption wrong. Chapter 3. Building an instrument to hear spacetime. Reassurance, the physics of detection. The specific instrument that would eventually detect Einstein's long-predicted ripples is called LIGO, the Laser Interferometer Gravitational Wave Observatory, and understanding precisely how it works requires appreciating both the elegant simplicity of its underlying core principle and the almost unimaginable, extraordinary engineering precision required to actually make that simple principle work in genuine practice. The fundamental underlying concept is, in its broad outline, reasonably straightforward. If a gravitational wave passes through a given region of space, it should, according to the theory, very slightly stretch space in one specific direction, while very slightly compressing it in a perpendicular direction, before the pattern reverses, oscillating back and forth as the wave itself continues passing through. If you could precisely, continuously measure the exact distance between two objects positioned along each of those two perpendicular directions, you should, in principle, be able to detect this specific oscillating pattern of stretching and compressing as the gravitational wave passes directly through your specific detector. LIGO accomplishes this precise measurement using a specific technique called laser interferometry. Each LIGO detector, and there are two identical detectors, one located in Hanford, Washington, and the other in Livingston, Louisiana, a deliberate design choice we will return to shortly, consists of two long perpendicular tunnels, called arms, each extending precisely 4 kilometers in a straight line, arranged in a large, precise L shape. A single, highly stabilized laser beam is split at the exact corner where the two arms meet, sending one half of the beam down each of the two perpendicular arms. At the far end of each arm, the beam reflects off an extraordinarily precisely engineered mirror and travels back to the same central corner point. If both arms are, at that specific moment, exactly the same physical length, the two returning laser beams will recombine in a very specific, precisely predictable way based on the exact known wavelength of the laser light being used. But if a gravitational wave happens to be passing directly through the detector at that specific moment, one of the two arms will be very slightly momentarily stretched, while the other is very slightly simultaneously compressed. This tiny momentary difference in the two arms' actual physical length causes the two returning laser beams to recombine very slightly differently than they otherwise would, producing a small, precisely measurable change in the resulting combined light pattern, a change that sufficiently sensitive detectors can, in principle, successfully register. The specific magnitude of the length change LIGO is actually designed to detect is genuinely, almost unimaginably small. A gravitational wave from a genuinely significant, energetic astronomical event might change the actual physical length of LIGO's 4-kilometer arms by an amount smaller than 1/10,000th the diameter of a single proton. To offer some sense of scale for that specific number, if you were to scale up one of LIGO's 4-kilometer arms to the actual distance between the Earth and the nearest star beyond our own Sun, the specific length change LIGO is designed to detect would correspond to a change smaller than the width of a single human hair. Achieving this level of extraordinary measurement precision required overcoming an entire series of formidable, genuinely difficult engineering challenges. The mirrors themselves needed to be isolated with extraordinary care from virtually every conceivable source of external vibration, passing traffic, distant seismic activity, even at the most sensitive level, ocean waves breaking against a distant shoreline hundreds of kilometers away. The laser itself needed to be stabilized to an extraordinary degree of precision. The entire 4-kilometer length of each arm needed to be maintained at an extremely high vacuum to prevent even individual air molecules from meaningfully scattering or otherwise disturbing the precisely calibrated laser beam as it traveled back and forth. And critically, two entirely separate, geographically distant detectors were deliberately, specifically required, not merely one. A single detector, however sensitive, could never fully rule out the possibility that a measured signal was actually caused by some purely local disturbance, a nearby earthquake, passing traffic, or even, at the most sensitive operational level, a large truck driving past on a nearby road. But a genuine gravitational wave, arriving from some distant astronomical source, would pass through the entire Earth and should, therefore, be independently detected by both geographically separated observatories within a very brief, precisely predictable window of time, determined by the finite speed of light and the exact physical distance separating the two specific detector sites. The two LIGO detectors, positioned in Louisiana and Washington states specifically, began operating in their earliest configuration in 2002, though this initial configuration proved, as expected by its own designers, insufficiently sensitive to detect any genuine astronomical signal. Over the subsequent decade, the entire detector system underwent a series of extensive, painstaking upgrades, collectively called Advanced LIGO, dramatically improving its overall sensitivity by a very substantial margin. Advanced LIGO officially began its very first formal observing run on September 12, 2015. 2 days later, before the collaboration had even fully completed its own official calibration procedures, the detector heard something. Chapter 4. The morning everything changed. Anomaly 1, September 14th, 2015. At 9:45 Coordinated Universal Time, the LIGO detector in Livingston, Louisiana, registered a distinct, structured signal, 7 milliseconds later, precisely consistent with the finite time required for a gravitational wave traveling at the speed of light to cross the physical distance separating the two detector sites. The LIGO detector in Hanford, Washington, registered an almost perfectly identical signal. The specific signal rose steadily in both frequency and amplitude over a period of approximately 0.2 of a second before terminating abruptly. This very specific pattern, a signal that gradually increases in both pitch and intensity before suddenly stopping, is precisely exactly what general relativity predicts should occur during the final moments of two extraordinarily massive, extraordinarily compact objects, such as black holes, spiraling into one another and ultimately merging into a single object. As two massive objects orbit each other, general relativity predicts they should continuously radiate away a small amount of orbital energy in the specific form of gravitational waves. This continuous energy loss should cause the two objects to gradually spiral closer together over time, which in turn should cause them to orbit each other correspondingly faster, which in turn should cause them to radiate away gravitational wave energy at a still greater rate. A self-reinforcing, accelerating process that continues right up until the two objects finally catastrophically collide and merge into one. This specific predicted pattern produces an extremely distinctive gravitational wave signal, a wave that rises in both frequency and intensity as the two objects spiral increasingly closer together, culminating in a final, especially intense burst of gravitational radiation at the exact moment of merger, before rapidly settling down as the newly formed, single combined object gradually stabilizes into its own final, stable configuration. This distinctive pattern is technically referred to as a chirp, owing to its close audible resemblance, once appropriately converted into sound, to the rising call of certain birds. When members of the LIGO scientific collaboration carefully analysed the precise details of the specific detected signal, comparing it directly against an enormous pre-computed catalogue of theoretically predicted gravitational waveforms generated through years of painstaking supercomputer simulation of precisely this kind of black hole merger event, they found an almost perfect, extraordinarily precise match to a specific, particular scenario. Two black holes with respective masses of approximately 36 and 29 times the mass of our own Sun, spiraling into each other and finally merging at a distance of approximately 1.3 billion light-years from Earth. The final merger itself, according to the detailed analysis of the recorded signal, released a genuinely staggering quantity of energy, equivalent to converting approximately 3 entire solar masses directly into pure gravitational wave energy in a period of less than a single second. For that brief, fleeting moment, the event radiated more raw power, in the specific form of gravitational waves alone, than the combined electromagnetic light output of every single star in the entire observable universe put together. And yet, because gravitational waves interact so extraordinarily weakly with ordinary matter, the very same fundamental property that makes them so genuinely difficult to detect in the first place, that almost unimaginably immense burst of energy passed directly through the entire physical body of the Earth, and through every single person on it, entirely unnoticed, except by two extraordinarily sensitive laser instruments in Louisiana and Washington state, specifically built and painstakingly calibrated to listen for precisely this kind of signal. The event was subsequently formally designated GW150914, a fairly plain systematic label directly derived from the specific date of detection, September 14th, 2015. Somewhere within the LIGO scientific collaboration, the specific event soon also acquired a considerably less formal, more affectionate nickname, one that quickly spread throughout the field. The event, spoken with a very deliberate, distinct capital E, as though there had never been, and truly could never quite be again, any other event remotely comparable to it. Chapter 5. Making absolutely certain. Anomaly. 2. The months of careful verification. A signal this genuinely extraordinary, quite possibly the very first direct detection in the entire history of human science of an entirely new fundamental way of directly observing the universe, demanded an extraordinary, correspondingly rigorous degree of careful scientific verification before any public announcement could reasonably be made. The LIGO scientific collaboration, comprising more than 1,000 individual scientists distributed across numerous countries and research institutions worldwide, spent approximately 5 full months carefully, systematically working to rule out every conceivable alternative explanation for the specific signal before finally feeling sufficiently confident to announce their detection publicly. The very first, most immediate concern was the specific possibility of what physicists within the field somewhat wryly call a blind injection. A deliberately, artificially inserted fake signal, specifically introduced into the detector's data stream by a small team of collaboration members, intentionally kept confidentially separate from the broader research team as a specific, dedicated method for rigorously testing the collaboration's own overall detection and analysis procedures, without the majority of researchers actually knowing in real time whether any specific signal was genuinely real or intentionally simulated for testing purposes. This particular practice, though scientifically valuable and rigorous, had, on at least one earlier occasion, caused a previous, considerably more preliminary gravitational wave collaboration to briefly, mistakenly believe it had made a genuine detection, only to subsequently discover the specific signal had, in fact, been a deliberately inserted test case all along. The LIGO collaboration moved swiftly and carefully to definitively rule out this particular possibility for the September 2015 signal. The dedicated blind injection system, it was confirmed, had not yet even been fully activated at the specific time the signal was detected. The event was not, and could not have been, an artificially inserted test signal. The collaboration then moved to systematically, carefully rule out every other conceivable source of instrumental or environmental interference. Could the signal have originated from some specific localized environmental disturbance? A distant earthquake? Unusual atmospheric weather conditions? Some form of unexpected human-caused activity near either specific detector site? Detailed environmental monitoring records from both sites, covering the exact relevant time period, showed absolutely nothing unusual whatsoever occurring at either location. Could the signal instead have originated from some specific internal electronic or instrumental malfunction? Extensive, systematic testing of every individual component within both detector systems revealed no plausible internal source capable of producing a signal with precisely the same very specific, very particular waveform pattern independently, coincidentally at both physically separated detector sites. Perhaps most critically and decisively of all, the collaboration performed a rigorous statistical analysis specifically designed to determine the overall probability that a signal displaying these exact particular characteristics could have arisen purely by random chance from ordinary background instrumental noise alone, rather than genuinely originating from any real astrophysical source. The final result of that detailed statistical analysis was extraordinary. The probability of this specific signal arising from random noise alone was calculated at less than 1 in 3 million, corresponding to a statistical confidence level exceeding 5 standard deviations, the same generally accepted, rigorous statistical threshold conventionally required within particle physics before any new phenomenon is formally, officially declared a genuine scientific discovery on February 11th, 2016, nearly 5 full months after the original detection itself. The LIGO scientific collaboration formally publicly announced the result at a carefully coordinated joint press conference. The specific announcement was met with immediate, widespread and entirely justified excitement throughout the global physics community and considerable attention well beyond it. Newspapers worldwide ran the story prominently on their respective front pages. Physicists who had personally spent entire multi-decade careers specifically working toward this singular moment were recorded, on camera, visibly, openly weeping with emotion during the announcement itself. 3 of the LIGO collaboration's founding scientists, Rainer Weiss, Kip Thorne, and Barry Barish, were subsequently awarded the Nobel Prize in Physics in 2017, formally recognizing their decades of foundational, painstaking work that had ultimately made the entire detection genuinely possible. Gravitational waves, first carefully, tentatively theorized by Einstein exactly 1 century earlier, had finally, definitively, been directly detected. An entirely new, fundamentally different way of directly observing and studying the universe had, at that specific moment, formally, genuinely begun. Chapter 6. A different way of listening to the cosmos. Anomaly 3. What gravitational waves actually reveal. The genuine lasting significance of that specific September 2015 detection extends considerably further than simply confirming Einstein had, once again, been correct about a specific century-old theoretical prediction. It fundamentally, permanently opened up an entirely new field of astronomy. One built not on the detection of light in any of its various forms, but instead on the direct detection of gravity itself in dynamic, active motion. Every single method of astronomical observation that came before gravitational wave detection, optical telescopes, radio telescopes, X-ray observatories, every single specific technique we have carefully discussed throughout this entire series so far, fundamentally depends on detecting electromagnetic radiation of one particular kind or another. This specific dependence carries certain genuine inherent limitations. Electromagnetic radiation can be absorbed by intervening dust and gas. It can be scattered, deflected, or entirely blocked by intervening matter positioned along its path. And perhaps most significantly of all, many of the most extraordinarily violent, most energetic events occurring anywhere within the universe, including quite specifically the direct collision and merger of 2 black holes, produce by their own fundamental physical nature no electromagnetic radiation whatsoever. Black holes, as we discussed at considerable length in an earlier chapter of this series, do not themselves emit light. 2 colliding black holes merging together remain, throughout the entire violent process, completely and totally invisible to every single conventional telescope ever built or conceivably buildable. Gravitational waves operate according to an entirely different set of underlying physical principles. They are not absorbed or meaningfully scattered by any intervening matter. They pass essentially unimpeded directly through gas, dust, and even entire solid planets, arriving at any given detector essentially unchanged from the moment of their original creation. And, critically, they are generated directly by the motion of mass itself, regardless of whether that specific mass happens to emit any light whatsoever. A pair of merging black holes, entirely invisible to every conventional telescope across the entire electromagnetic spectrum, nonetheless generates an extraordinarily powerful, clearly detectable gravitational wave signal. This means gravitational wave astronomy offers a genuinely, fundamentally new and different window into observing types of cosmic events that were previously, in an important and quite literal sense, completely invisible to human science. In the years immediately following that initial historic 2015 detection, the LIGO collaboration, subsequently joined by an additional European gravitational wave detector called Virgo, and later still by an additional detector in Japan called KAGRA, went on to detect numerous additional gravitational wave events. The great majority of these subsequent detections involved further black hole mergers, broadly similar in overall character to the original historic 2015 event, though each one, upon careful individual analysis, offering its own unique specific insights into the general overall population and distribution of black holes throughout the observable universe. One particular subsequent detection proved especially genuinely significant. On August 17, 2017, the LIGO and Virgo collaborations jointly detected a gravitational wave signal originating not from two merging black holes, but instead from two merging neutron stars, the extraordinarily dense stellar remnants we discussed in an earlier chapter of this series, produced by the supernova explosion of a massive star. Unlike black hole mergers, a neutron-star merger event was specifically expected, based on established theoretical models, to also produce a significant detectable burst of electromagnetic radiation, particularly in the specific form of gamma rays. Remarkably, precisely such a corresponding gamma-ray burst was independently detected by an entirely separate space-based observatory, occurring within less than 2 seconds of the LIGO-Virgo gravitational wave detection. This specific correspondence prompted an immediate, coordinated, worldwide observational effort, with dozens of telescopes across the entire globe rapidly redirecting their attention toward the same specific region of sky, successfully observing the same singular cosmic event across an extraordinarily wide range of different wavelengths simultaneously. Gravitational waves, gamma rays, X-rays, ultraviolet, visible light, infrared, and radio waves, all originating from the exact same singular astronomical event. This specific coordinated multi-wavelength observation, now generally referred to within the field as multi-messenger astronomy, represented an entirely new, fundamentally more comprehensive way of directly studying individual cosmic events by simultaneously combining information gathered through gravitational waves together with more conventional electromagnetic observations. Among a great many other genuinely significant scientific results, this specific 2017 neutron-star merger event provided the very first direct, unambiguous observational confirmation that the collision and merger of two neutron stars is indeed a primary astrophysical site where many of the universe's heaviest elements, including gold and platinum, elements we discussed in the immediately preceding chapter of this series, are actively forged through precisely the same fundamental rapid neutron capture process we described in that earlier chapter, though here occurring within an entirely different, distinct astrophysical setting than a standard supernova explosion. Gravitational wave astronomy, in barely more than a single decade since its own historic initial 2015 detection, has already fundamentally substantially transformed our overall scientific understanding of black holes, neutron stars, and the specific violent, catastrophic ways in which the universe's heaviest and most extreme objects ultimately interact and collide with one another. Chapter 7. What the ringing might still tell us. Speculation spiral. Gravitational wave astronomy remains even now a genuinely young and rapidly developing scientific field, and several profound, genuinely open questions remain actively, energetically under active investigation, with the tantalizing possibility that gravitational wave observations specifically might ultimately provide the decisive, deciding evidence needed to resolve them. One particularly compelling, actively pursued possibility concerns the specific search for gravitational waves originating from the Big Bang itself. If cosmic inflation, the theory of extraordinarily rapid early universe expansion we carefully discussed in an earlier chapter of this series, genuinely did occur, current theoretical models predict it should have generated its own distinctive characteristic background of primordial gravitational waves, dating from the very earliest moments of the universe's entire existence. Detecting this specific, extraordinarily faint primordial gravitational wave background would provide direct, remarkably compelling evidence for cosmic inflation, potentially even allowing physicists to directly probe physical conditions occurring at energy scales far, far beyond anything that could ever conceivably be recreated within any particle accelerator here on Earth. Current gravitational wave detectors, including LIGO, are not yet sufficiently sensitive to detect this particular, extraordinarily faint predicted signal, but future next-generation detectors, including a large planned space-based observatory called LISA, specifically designed to detect gravitational waves at much lower frequencies than LIGO can currently access, may prove capable of eventually detecting it. A second, closely related and profound open question concerns the specific interior structure of neutron stars. When two neutron stars collide and merge, as occurred in the notable 2017 event we discussed a moment ago, the extremely precise, detailed characteristics of the resulting gravitational wave signal encode subtle, specific information about the exact internal physical structure of the two colliding neutron stars themselves. Information regarding the precise behavior of matter compressed to genuinely extraordinary densities, conditions that could never possibly be recreated or directly studied within any laboratory here on Earth. Careful analysis of an increasingly large growing catalogue of detected neutron star merger events may eventually help physicists resolve long-standing, genuinely difficult open questions concerning the precise physical behavior of matter under such genuinely extreme conditions. A third area of genuinely active ongoing research concerns the specific search for entirely unexpected, unanticipated gravitational wave sources, genuinely novel astrophysical events that do not neatly correspond to any previously known, previously catalogued category such as black hole mergers or neutron star mergers. Some theoretical physicists have specifically proposed that gravitational wave detectors might, in principle, eventually be capable of directly detecting entirely different classes of cosmic events altogether, including, quite speculatively, potential signals originating from cosmic strings, hypothetical, currently unconfirmed topological defects theorized to have possibly formed during the extremely early universe, or even, in certain highly speculative theoretical scenarios, direct evidence relevant to the still unresolved nature of dark matter itself, a mystery we explored in considerable depth in an earlier chapter of this series. None of these particular, more speculative possibilities has yet been confirmed through any actual observation, but the specific history of gravitational wave astronomy as an active scientific field, even across its relatively brief decade of existence so far, has already repeatedly demonstrated a clear, consistent pattern. Each individual new detection has, so far, reliably tended to reveal genuinely useful, often previously unanticipated scientific information, well beyond what researchers had originally, specifically anticipated finding at the outset. There remains no strong, principled reason to confidently expect this general, well-established pattern will not continue well into the future, as gravitational wave detectors themselves continue improving steadily in overall sensitivity, and as the accumulated catalogue of individually detected events continues to grow correspondingly larger. Chapter 8: A Century of Waiting for Confirmation. Context and History. The specific, extended century-long gap separating Einstein's original 1916 theoretical prediction and gravitational waves' eventual, actual 2015 direct detection offers a genuinely worthwhile, instructive final piece of broader historical context, one that connects meaningfully to several other individual stories we have carefully explored throughout this entire series. Direct, unambiguous confirmation of gravitational waves' genuine physical reality did not, in fact, first arrive through LIGO's landmark 2015 direct detection. It arrived considerably earlier through an important, indirect but highly convincing line of observational evidence discovered several decades prior in 1974. In that specific year, astronomers Russell Hulse and Joseph Taylor discovered a genuinely remarkable astronomical system, two neutron stars orbiting one another in a notably tight compact orbit, with one of the two specific neutron stars additionally functioning as what astronomers call a pulsar. A rapidly, extraordinarily precisely rotating neutron star that regularly emits a narrow, highly consistent beam of radio waves sweeping past Earth with each individual rotation, functioning in effect as an almost impossibly precise natural cosmic clock. Because this specific pulsar's individual rotational timing could be measured with such extraordinary precision, Hulse and Taylor were able to measure the precise orbital period of the entire binary neutron star system with equally extraordinary precision. Over the course of several subsequent years of continued careful observation, they discovered something genuinely significant. The system's measured orbital period was very gradually but consistently and measurably decreasing over time, meaning the two neutron stars were slowly, steadily spiraling closer together, exactly as general relativity specifically predicted should occur if the entire system were continuously radiating away a portion of its total orbital energy in the specific form of gravitational waves. The precise measured rate of this specific orbital decay matched general relativity's own theoretical prediction with genuinely remarkable, striking accuracy. While this particular result did not constitute a direct detection of gravitational waves themselves in the same specific sense LIGO would later achieve, it provided extraordinarily strong, compelling indirect evidence that gravitational waves must indeed be real and must genuinely carry real, measurable physical energy away from their originating source, exactly as Einstein's original theory had specifically predicted decades earlier. Hulse and Taylor were subsequently awarded the Nobel Prize in Physics in 1993, specifically recognizing this particular discovery. This entire specific historical sequence, an initial theoretical prediction, followed by decades of genuine scientific uncertainty regarding its ultimate physical reality, followed eventually by indirect confirming evidence, followed still later by direct, unambiguous detection, closely, recognizably echoes a broader historical pattern we have now encountered repeatedly throughout this entire series. Black holes were similarly first theoretically predicted through Schwarzschild's specific 1915 mathematical solution, decades before they were finally directly confirmed through actual observational evidence. The expansion of the universe was likewise first theoretically anticipated through Einstein's own original equations, before Hubble's subsequent direct observations definitively confirmed it. Dark matter was first inferred entirely indirectly through its measurable gravitational effects on visible matter, long before any hypothetical direct detection of the underlying dark matter particles themselves. Modern physics, viewed collectively across this recurring historical pattern, frequently operates according to this same broad, consistent sequence. Mathematics reveals a genuinely surprising, often deeply counterintuitive possibility. Physicists subsequently, sometimes for many years or even decades, remain uncertain whether that specific mathematical possibility corresponds to anything genuinely physically real. And then, eventually, sometimes only after an entire extended human lifetime has already fully passed, an instrument sufficiently sensitive and sophisticated is finally constructed to definitively settle the matter, one way or the other. Einstein passed away in 1955, 6 decades before LIGO's own historic direct detection, still genuinely uncertain by his own account, whether gravitational waves would ever be conclusively proven real, and, if they were, whether any conceivable instrument would ever prove sensitive enough to actually detect them. He did not live to see spacetime itself finally, conclusively confirmed to ring. Chapter 9. The universe has been ringing all along. Reckoning. There is something genuinely worth sitting with quietly in this particular story's specific distinctive shape, something that meaningfully distinguishes it from several of the other individual mysteries we have carefully explored together throughout this entire series. Gravitational waves are not some genuinely rare, unusual, or exotic cosmic phenomenon occurring only under highly unusual or exceptional circumstances. They are instead a direct, unavoidable, fundamental consequence of the very same basic physical laws that govern absolutely everything possessing mass, everywhere throughout the entire universe at all times. Every time any two objects orbit one another, two black holes, two neutron stars, two ordinary stars, even at an entirely negligible but technically non-zero level, the Earth and our own moon currently orbiting each other. They are, according to general relativity, continuously radiating away a small amount of gravitational wave energy, essentially all of the time. The universe, in this very real, quite literal sense, has been continuously, ceaselessly ringing in the specific form of gravitational waves for its entire 13.8 billion year history. We simply lacked, until remarkably recently, in the year 2015, any instrument even remotely sensitive enough to actually hear it. Think, for a moment, about precisely what that specific fact genuinely means. For the overwhelming majority of human history, for every single individual generation of humans who ever lived, going all the way back to our earliest common ancestors, the universe's gravitational ringing was occurring constantly, all around us, continuously, and entirely undetected. Ancient astronomers carefully observing the visible motion of planets across the night sky. Medieval scholars patiently debating the true, fundamental nature of the heavens above them. 20th century physicists first theoretically predicting gravitational waves' existence, then subsequently spending decades genuinely uncertain whether that specific prediction would ever be conclusively confirmed. All of them lived their entire respective lives immersed within a genuine, continuous cosmic symphony of gravitational radiation, one that remained, throughout all of human history until remarkably recently, entirely completely inaudible to our own species. We are the very first generation in the entire history of life on Earth capable of actually hearing it. That specific fact carries a particular kind of weight worth sitting with quietly at the close of tonight's specific episode. Every single scientific mystery we have carefully, patiently explored together throughout this entire series, the search for other life beyond our own planet, the precise, still unresolved expansion rate of the universe, the true underlying nature of dark matter, the deep, genuine mystery of what occurs at the exact center of a black hole, the honest, acknowledged limits of what we currently know regarding the universe's ultimate beginning, the complete life cycle of stars that ultimately, quite literally made you. Every single one of these individual mysteries has been explored and investigated using light, telescopes carefully, patiently gathering photons that have, in many specific cases, been traveling toward us for literally billions of years. Gravitational waves offer something genuinely, fundamentally different, an entirely separate sense altogether. Not sight in any conventional sense, but something considerably closer to a very particular, very specific kind of hearing. Direct physical vibrations in the fabric of space-time itself, arriving at our detectors not as light, but as motion, as vibration, as sound in only the loosest, most metaphorical possible sense. Humanity spent its first many thousands of years of careful astronomical observation exclusively watching the universe. In September 2015, For the very first time in the entire history of our species, we also began genuinely to listen. Tonight, as you finally drift towards sleep, space-time itself continues quietly ringing all around you, everywhere, all the time, exactly as it always, continuously has. Black holes are continuing to spiral into one another, somewhere out there in the vast surrounding darkness, right at this exact moment. Neutron stars are continuing to merge, releasing bursts of gravitational energy that will not arrive at our own planet's specific detectors for millions, or in many cases billions, of years yet to come. The universe's own vast, ongoing gravitational symphony continues playing, entirely uninterrupted, regardless of whether or not anyone happens to be listening. We are listening now. And what we have already heard, in barely more than one single decade of active listening, has already been genuinely extraordinary. We do not yet know precisely what we will hear next.